Hello. This video is going to be about strong collision resistance, and it seems intuitive to go ahead and start by describing strong collisions. So what exactly is a strong collision? Well, a strong collision is simply finding two messages, we'll call them M1 and M2, whose hashes are equal. So what this means is I can find any old two messages, doesn't matter what messages they are, doesn't matter the content, nothing. As long as their hash is matched, then we have strong collision. Okay. Now, how might this be useful to some sort of evildoer? Well, so assuming this is true, we found two messages hash to the same value, we can pick a victim, and if somehow we were able to talk this victim into signing, let's say we give them message 1 to sign. Let's say they go ahead and sign message 1. Well, so what is a digital signature? Work from the inside out here. Digital signature is a hash of a message that is encrypted, right? And we encrypt with private keys. So, if we talk this person into this message, M1, they hash it and then they encrypt the hash. So they also, let's say they send this back to us. This message may look something like, M1 concatenated to, all this signature. So we'll say, the encrypted hash of message 1. Okay. Then what we could do is we could take message 1 out of this message, stick message 2 into it, and send it, some third party here. We'll say, Joe. Okay. So what Joe will do is he will hash message 2, which has the same hash as message 1, right? Then decrypt the signature, right? So he'll use the public key of the victim to decrypt the hash of the message. Now, the hash of message 1 matches the hash of message 2. So what we just done is sent a message that is not able to be repudiated from the victim, but that is not the original message. So we've kind of broken non-repudiation here with our strong hash. Okay? So the intuitive question is probably, well, if you're finding just any old message 1 and any old message 2, what use are those really to us? What's the chance that they won't be anything but garbled junk, since you're finding any messages that hash, doesn't matter what they are. Well, you're right, but the point here is that we've broken non-repudiation, and that is a strong collision. Weak collisions are generally a little more useful to us, from an attacker sense, but that is a strong collision. And let me go ahead and clear this out here. Okay. So we've seen a strong collision attack. If we want to think of this more in maybe more friendly terms, in programming, the most analogous thing we have, a lot of us have taken analysis of algorithms and/or data structures and algorithms, DS&A. So, we can have a hash table, which is basically an array. So let's say in this case we have an array of 5 slots. We'll call it K. Our size K equals 5. And let's say that we plan to put 20 elements into this array. N equals 20. So that's a problem, right? We can't fit 20 elements into 5 slots. Not with what we know about an array. This is what we call the pigeonhole principle. Pigeonhole. And, let's say we have 5 holes or 5 cubby holes, 5 nests, or whatever for pigeons. We want to fit 20 pigeons in there. Well, we have more pigeons than holes or cubby holes or nests, right? So we'll need to have more than one pigeon in at least one hole, right? In this case, what the pigeonhole principle tells us is that we will need we will have at least one item, in this case slot, that has at least n over k elements in it. So in this case, we're talking, the ceiling of n over k is 20 over 5, which is 4. We'll have at least one slot that has at least 4 elements in it. And that much is intuitive to us, because if we look at this and we have a perfectly uniform distribution, if we want to put 20 elements in here, we'll have to have at least 4 elements per slot. So this is correct. Now, just really quickly to go over the function of a hash table, a lot of times what we'll do, we will resolve collisions via chaining, and what this means is we'll have a linked list in each one of these. So our linked list is made of nodes, and nodes have a pointer to the next element. So that way we can resolve collisions this way. If you want to see how it works, we could, let's say we want to put the elements 1 through 20 in here. Let's say we get element 17. One thing we can do, since we have 4 slots, we can modulus our input element by our size, which is 5. And that'll give us the slot that we hash to, right? Because we'll get values from 0 to 4. 0 to 4 inclusive. So in this case, 17 modulo 5 is a remainder of 2. So we would put 17 in 0, 1 slot 2. And this is slot 2 because the arrays are, indexed to 0. Let's say our next element is 8. 8 modulo 5 is 3. So 0, 1, 2, 3, here's 8. And if we want to see a collision and how we deal with the collision, let's say we get 12. 12 modulo 5 is 2, and we already have 17 is taking slot 2. So when 12 hashes to slot 2 also, well, we just chain, right? We put our next pointer to 12, and that way if we want to find, if we want to look up, hey, it must be in slot 2, say, okay, look at the first element at 17. No, that's not it. Look at that next element, 12. Oh, there it is. It's in our table. So that's just a kind of hash table of thinking about collisions and this pigeonhole principle. All right. And when we hash, we assume a random distribution. Speaking of random distributions, or I say uniform distributions. Hashing really isn't random. One input will give you one particular output. Unless it's salted and your salt is random, then this could vary. But so speaking of random distributions or uniform distributions, let me go ahead and put text here so I can be a little bit neater with this. A lot of the times you'll see birthday problem mentioned really in any discrete math text or cryptography text or combinatoric probabilistic text. Birthday problem. So the birthday problem, let's say we have X users, in this case, X people in a room. We'll say 5. We'll take a small number of people in a room. What is the probability of at least one of them having the same birthday? Okay, out of 5 people in a room, and we'll assume 365 years. We won't complicate this by saying 366 leap year or anything like that. So your intuition may be to say, I got this 5 over 365, since there are 365 days in a year. Well, that's wrong. That's wrong. 5 to 365 works out to be about 1.37%, but this is wrong, like I said. So what's right? Okay. So how do we calculate this? Let's go ahead. It's easier for us to start by calculating the probability of no collisions, no duplicate birthdays. And so let's take a look. Let's say we go into a room. We have a list with us, and we're with each person we interview, we're getting their birthday and we're putting it on the list. So the first person we come across, what's the probability that their birthday is not on this list? 100%, right? Because our list is empty. So we can express this as 365 over 365. This is 1 or 100%. And you'll see why we express it this way here shortly. Now, person 2 is a little bit different. Person 2, we already have a name. We already have a birthday on the list. That leaves us with 364 days left to choose from, well, that are remaining that will not cause duplicates, out of 365 days this person could have been born on. Same thing with person 3. Now we have 2 names on the list, and we're down to 363 free days out of any one of the 365 days they may have been born on. Same with person 4, 362, because now we were down 3 days, and person 5 lastly. Okay, so how do we combine these to kind of get this no duplicate, probability, if you will? Well, back to the coin flipping problem. This may not seem intuitive what to do here, but if you think back to the coin flipping problem, what's the probability of a coin coming up heads? 0.550%, right? We'll say that's the first try. What's the probability of it coming up heads, on any, let's say try number 2? Well, it's also 0.5. Same with try 3. Okay, and then if we want the probability of this in a row, 0.5, 0.5, 0.5, then we'll multiply them, right? We know that. 0.15 or 12.5%. So that's what we do here. We do the same here. So we'll come down here. All right, continue here. So what we do, so for our probability of no duplicates, we have 365 over 365 times 364 over 365 times 363 over 365 times 362 over 365 times 361 over 365. Whew. And that's a pretty big number, so let me take calc. All right, so you know what though? We have the probability of no duplicates. The probability of duplicates. Look back at our, this may be a little easier to see with our coin flipping problem, right? 0.125. So that means our probability of this not being true, if the converse, is going to be 0.875 or 87.5%, which is 1 minus 0.5 times 0.5 times 0.5, right? So this we want 1 minus all this stuff. So here we go. Let's let it rip. We are going to say 1 minus 365 over 365 times 364 over 365 times 363 over 365 times 362 over 365 times 361. This is our 5th guy. 365 times 100, 2.71%. So look at this. We had kind of guessed that, if we were to do it intuitively, 1.37, and we're actually about twice that amount. Now, look at this. I had to write a whole bunch of stuff here. This is really big. And imagine if I tried to find hash values. We're talking billions or trillions or quadrillions or even more. How would I write all this out? How would I express this? I can't possibly turn this into a workable, a workable calculation. So we can formalize this. Because let's see what we're doing. We have 1 minus 365 is n over n times n minus 1 over n times n minus 2 over n times n minus 3 over n times, that doesn't look like n times n minus 4 over n. Okay, and we'll take this over here. We'll say 1 minus, look at this. I got 1, 2, 3, 4, 5. I've got k n's down here. Right, so n k times, this would be n raised to the k, right? Up here I have n minus 1, n minus 2, n minus 3, n minus 4. So I have n times n minus 1, blah, 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 all the way out. That's a 1 to n minus k plus 1. right? And we can, we could do this as minus k plus 1, right? Keep in mind 0, 1, 2, 3, 4. So you have, since we're starting our indexing at 0, if you will, that's sort of like an array, if you want to think of it that way. An array of size 5 only has, up to addressable element 4. Okay, so that still isn't too pretty. I don't know what I'm going to do with that. Yeah, I do. All right, watch this. 1 minus. Actually, we'll take a side step here. Watch this, real quick. This is related. Trust me. N equals 8. K equals 5. So we're going to go ahead and do this here. We're going to use this stuff right here. We're going to say 8 times 7 times 6 times 5. Hold on. N minus k plus 1. 8 minus 5 is 3 plus 1, 4. Okay. Here we go. 8, 7, 6, 5, 4. So watch this. All right. This is n times n minus 1, blah, 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 to n minus k plus 1. Watch this. What happens if I do this? It's all the same, right? It's all the same. Because, see, I haven't changed the answer. My 3's and my 2's and my 1's cancel. So this is equivalent. Now, this is handy because, look at this. This is 8 factorial, right? 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 8 factorial. What's this? This is n minus k factorial, right? All right. So now we're able to clean this up even more. So we got, we'll say this is, n factorial over n minus k factorial. You see where I'm coming from. All right. So 1 minus n factorial over n minus k n to the k. Let's do this a little more there we go, to the k, so we can see it's a superscript. And if you remember from algebra, this is the same as 1 over n factorial, or 1 minus, rather, n factorial over n to the k times n minus k factorial. Whew. All right, so that's our formula there. What does this allow us to do? Remember, we had to write a whole bunch of stuff here. And that's why I only chose 5, I knew where this was going. That's why I only chose 5 people, the example of 5 people earlier. So I can I can go ahead and I can have no fear now that I have the formula. Watch this. I can, let's say 20 people. 1 minus, my n is still 365. N to the k, my k is going to be 20 since I have 20 people, right? Times n minus k, 365 minus 20 is 345. Oops. Factorial. Whew. That's a big, big, big number. I'm going to have to go to Wolfram for this. My calc won't handle that. All right, and 1 minus 365 factorial divided by 365 to the 20th times 340 factorial. Survey says 41%. So, our intuition would have been way off here. If we had said 20 people, darn. If we had said, we got this 20 people, 365 days, hey, 5.4%. No, we're way off. And this is because, if we look at this intuitively, this is because we're reducing our possibility size, our universe, our space of values here with each successive try, with each successive item. And that's why this works out this way. Now, there's one more thing. If you look at a lot of discrete math or whatever texts, if anybody talks about the birthday problem, they only tell you, you only need 23 people in a room for the to be likely that you have, a duplication of values, addition of birthdays, rather. Okay, so let's change this to k equals 23, excuse me, 23, and then 365 minus 23 is 342, because look, 1 minus 365 factorial over 365 to the 23 times 342 factorial for 23. And we should be just over 50%. Yep, 50.7%. Okay, so that's where that 23 comes from. Okay. So how does the birthday paradox, how does the birthday problem relate to hashing? Well, let's say that we have a hash function that has an output of 32 bits. And so that means we'll have a universe of 2 to the 32 output, so our output size. And let's say that we have a machine that can feasibly compute, I don't know, 2 to the 16th, make it nice and neat, 2 to the 16th hashes. Okay, that's a tiny number. That's 65,536. So that's a tiny number, but yeah, I want to keep these numbers manageable so that we can still crunch them, so that Wolfram doesn't complain about computation time exceeded or the size of the numbers to me. So in this case, our n, our hash universe size is going to be 2 to the 32nd. Our k that we're trying to create a duplicate on, or see if we can create the probability of creating a duplicate, a collision on, is 2 to the 16th. Okay, so what is the probability that with 65,536 hashes we can generate one that will collide with one of these 4 billion something known outputs? That's how much 2 to the 32nd is. Okay, remember our formula, 1 minus n factorial. Man, these are getting big. Over, what do we say, n to the k. This is a ridiculous number here too. 2 to the 32nd to the 2 to the 16th times n minus k factorial. Man, that's a big number. All right, let's see. We definitely have to go to Wolf for this one, and hope that it'll crunch it for us. 1 minus 2 to the 32nd factorial divided by 2 to the 30. Oh darn! 2 to the 32nd. To the 2 to the 16th times 2 to the 32nd minus 2 to the 16th factorial. Wow, so 40%, 39, 40%, right? So we don't have to generate too many. You see the difference in the two numbers. This is only 65,000. This is 4 billion. Right, over 4 billion. Okay, so collisions are, they may not be feasible in some circumstances, but they're definitely not impossible. In this case, they are very feasible. This is why we don't use 32-bit hash functions anymore. We're up to, I guess if you use your hash 1, we got 160 and even, alternatives. So, yeah, we were about in the ballpark. We had about 5%. If you look in a lot of texts, here in the text, you see the number 2 to the n over 2 thrown around. And if you look, that's pretty much true. See, our n is 2 to the 32nd. 2 to 2 is 2 to the 16th, right? And we see that we're just about likely to generate a strong collision with 2 to the n over 2. And with, weak collisions, different. It's 2 to the n. So what this means is that it's going to be hard to protect against, right? It's going to be quadratically harder to protect against a strong collision hash. I hope this helped. Rather than hindered. So we talked about, we'll just quickly, review what we talked about here. So we define collisions are basically, finding any tool messages that hash to the same. We could do an attack such as, trick somebody into signing a message that hashes to a certain value, replacing it with another message that hashes to another value, and sending it. Therefore, their non-repudiation is broken. We looked at, hash table, which is kind of the, analog programming to hashing. We saw collisions. We saw how collisions are resolved there. We talked about the pigeonhole principle. you know, we're assuming uniform distribution here on these values. We talked about the birthday paradox, and you know, we saw kind of what correlates to collisions, and you know how our collision probability increases non-linearly with our you know, with our input size, and it's because we're reducing, you know, our space of possibilities with each new attempt. We reduce the possibility space by 1. Okay, so all right, hope this helped. See ya.